because since you're recorded and it's on YouTube, we just need the thanks. Thank you.
Hi. Hi. So nice. Perfect. Nice to meet you. Thanks, Birmingham. Morning, everybody. Thursday morning. Get the light crowd. So today I'm going to talk about both securing and assuring real-time communication. So for those of you that don't know, at Sonus, effectively, we build large-scale carrier-grade real-time communication systems, right? And as the technology has shifted from a hardware to a software world, we've shifted with it. So basically what I'm going to share this morning is more of our journey and basically what we've learned along the way more than anything, so that you can effectively understand how to avoid those pitfalls and how to actually effectively get real good performance and high security in a virtualized environment. So I'll start off talking about packet processing in an NFV environment, and then dive into real-time security side of it, and then I have a small demo as well that'll show how we're actually coordinating with firewalls. This, just up front, it will be fairly fast-paced. I normally do this in about an hour, and it's into 25 minutes, so we'll see how it goes. Apologies, let's see, the slides are not advancing. Fix that. There we go. And take it from there. So ultimately, when you come to run a hardware-based real-time processing communication system in software, it's very different to typical virtualization. And the reason for that is when virtualization was built, it was ultimately mostly for web scale traffic, right, and for IT, traditional IT roles. So not delay sensitive, not latency sensitive. You know, if your email arrived a couple of seconds late, nobody noticed. If a web page gets a little bit of a delay in the initial connection setup, nobody noticed. However, when you come to do real time, if your packets are not processed predictably and effectively, efficiently, you end up with very high latency. And very high latency equals poor user experience, and effectively the whole thing falls apart. So we've done a lot of work on top of OpenStack and tuning OpenStack so to be able to build private clouds and then also running in public clouds as well to be able to effectively optimize and make it work, right? And getting that deterministic low latency behavior. So unless you actually tune it for that environment, it really doesn't work as it needs to for real-time communications. There's been a lot of advances in OpenStack and a lot of advances actually in the different virtualization technology, especially in the last, I would say, 2 to 3 years, that have really made this possible. And the combination of enterprises who really went to virtualization first, and then now the service providers pushing that together really has actually allowed that to go forward. And the open source community have done a really good job too. And and organizations like this actually have done a really good job too of actually pushing that forward. So we've tuned up OpenStack, and I'll talk you through exactly what we did there. We're also leveraging microservices, which makes a lot of sense in the modern, basically cloud scale world. Didn't make sense in hardware, but it makes sense in that. And we're using graphical processing units, GPUs, from NVIDIA and Intel to really get that same scale that we did out of the digital signal processors. So part of the challenges, first of all, VirtIO. You guys familiar with VirtIO? So effectively, it's a very clever way of solving the hypervisor problem when it comes to I/O. In the past, we always had to have the full network driver in the guest OS. Now we're effectively saying no. If the guest OS knows it's running under hypervisor and actually effectively uses a driver that's optimized for that, you can now actually make decisions and only put small layers. Instead of having all the layers up the Mac layer, you can now put just a small amount in there. So VirtIO really gives you a much higher performance than you would if you were just running a full network sitting inside the hypervisor and effectively within the orchestrated environment in OpenStack. A couple of challenges with it though. So CPU pinning, which we have to use CPU pinning within a real-time environment because otherwise the packet processing is too unpredictable. Because effectively the scheduler will send out the different packets to different processors, and you end up with them coming in a different order, and the jitter buffer ends up growing, and you end up with a really poor user experience. So we have to pin it. However, when you pin it, you effectively end up with a locks happening, right? And then you effectively Kumu's stalling out the processor. You end up with really what's normally typically in Ethernet, a short queue of only 256 bytes. And it's non-configurable, but that's a big issue in this because now what's happening with the packets coming out of order, you end up growing the queue and overflowing the queues. So when you overflow the queues, now you end up with not only poor experience, you actually end up with failing calls, drop calls, etc. And then making matters worse, because you're running under, effectively a split architecture, for every data packet, there's actually a signaling packet. So you're halving the efficiency. So it does it 2 to 1. So effectively, you only get a queue size of 128 bytes because you're sending literally data and control for every single one. So put those all together and you end up with a really, really poor user experience. So it basically just goes crashing into the ground and really doesn't scale well. And this is why a lot of people initially said, no, there's no way you can actually run it. Now all of that was not a problem, as I said, in non-real-time environments, but in real-time environments, it's a massive issue. So solving it effectively is effectively within OpenStack Pike, so the latest version of OpenStack, there's now the ability to actually set different cores for the different emulator threads. So you no longer have, when you pin a CPU, you no longer actually have the controls running on that same. You can now also modify the timings within OpenStack, and you're able to enable the multi-packet processing as well, which improves the throughput. So making those changes, right, pinning the CPU, basically reducing the timings, and adding the parallel packet processing basically gets us about a 2 times improvement. So additional improvements that we actually do within the So just to kind of break down some of the pieces that we enable with an OpenStack to tune this. So enabling huge pages, so that now instead of just sending effectively small pages of memory up to the guest OS through the hypervisor, sending a huge page through, gave us about a 10% latency improvement. Forcing the BIOS to turn off speed step, putting it to maximum performance, and effectively making it so that it is running at top speed all the time, because with real time you really don't want effectively the speeds varying. That gave about a 20% improvement. NUMA boundaries, so effectively the address space within the multi-core CPU, right? Because even though we have these massive servers now that have huge amounts of memory and huge number of cores, you have NUMA boundaries, which is basically address space boundaries within them, that if you go across it, now you're actually you've got a good chance you're going to have cache misses, and you've got a good chance you're going to have to use a shared bus. So it slows it down a lot. So by actually saying no, keep the real-time processing within a particular NUMA boundary makes a massive difference. So 50% improvement by actually making the system NUMA aware. Pinning the CPU, as I mentioned, because you effectively are running real-time, if you don't pin it, you end up with a lot of distributed packets running on different cores, and it really holds down. That made also a massive difference. So 50% improvement. And then CPU mode. So what this is effectively pushing through the actual characteristics of the CPU from the host OS to the guest OS, so that the guest OS can actually use the optimizations that are known about that particular processor. So that's a particular model number, etc. Made a 30% improvement. So by tuning all these different factors, we effectively found we were able to improve the latency and the throughput by 5 to 6 times. So significant improvement. What's really pretty amazing too is the throughput, effectively the latency drops, right, which of course improves the experience. It also improves the throughput, so you're able to get a much higher call per second rate and a higher number of simultaneous calls, simply because you're able to process them quicker, you're using up less CPU cycles, so it's a win-win all throughout. So just by tuning those few parameters with an OpenStack, that really allows a huge amount of throughput. So my main objective this morning is to share these findings, right, because I think it's very important for us in the real-time community to know that, yes, it is possible, right? Yes, up until now, we've done a lot with NFV when it comes to doing firewalls, routers, etc. But it is totally possible to also run real-time voice, video, provided you optimize and configure it correctly. Microservices. So when SBCs, which is what our core businesses, were developed, it made a lot of sense when you were developing on hardware to basically put everything onto one box. Why? It made it simpler, right? Rather than having different components, you would need different pieces of hardware to do it. The gateway space had gone through that gyration of having split signaling and media, but with building an integrated system made it just much simpler. And customers loved that because it was one less thing to configure, there were less things to go wrong, it was a usable, scalable system. However, now that we've moved to the cloud, and effectively you can actually distribute components in different places in the cloud, plus we've also got different requirements for signaling and media, right? With video, effectively you can have a lot more use of resources and a lot more different streams than you would if it's just a one-to-one audio call, right? Or a signaling could have no media resources. So it makes a lot of sense now to actually pull them apart, right? And within a microservices architecture, you can make stuff a lot more flexible. So we've taken our SBC and we've actually pulled it apart into a signaling SBC, a transcoding SBC, and a media SBC. And we do a best of breed scenario. So we can, from a transcoding perspective, we can use a regular x86. I don't recommend it. The performance is really, the cost per watt is not really there, but you can use a regular x86. We can do it on hardware, so you can use an existing, if you have an existing piece of equipment from us or our competitors, you can use that. You can use GPUs, and I'll talk more about that in a second. So effectively using graphical processing units to be able to do the transcoding. And then on the packet processing side, you could use a traditional x86, or you could use the network processors in the hardware, or you could use an SDN-based network to be able to control it. We can also, too, use RFC 4117 to be able to do transcoding as well. Right, so by breaking it apart, you can now effectively have that panacea of multiple vendors being able to scale to multiple places and get the best of all worlds. So once you've broken it apart, we pushed we pushed into Amazon, Google Cloud, Azure, and of course into OpenStack for the private clouds, and said, well, how do we get the same performance for audio transcoding? And a lot of people go, well, why are you still transcoding? What do you need to transcode for? Well, the reality is, with the evolving codec world that we live in, even the latest and greatest software that's out there, whether it's going from Opus to go to the G711, so coming from WebRTC, or if it's coming from a Scout for Business running Silk, there's still many, many differences in codecs, right? So what we did is we said, how do we take the performance that we got in DSPs, which up until this point provided the best possible performance to do transcoding, and get the same equivalent within the cloud? And the way that we did that is said, well, what architecture looks closest to a DSP? And it's a GPU. GPUs are highly vectored, lots of little cores. You're able to split across lots of processors across it. So by taking our DSP code, porting it over to GPUs, we were able to see massive performance improvements over what we saw in x86. x86 typically would, I haven't actually shown it on this particular graph, but it's kind of down in the 10% kind of scenario here. So as a baseline, we use the NVIDIA K80 GPUs. That's the 100% baseline, and this is a G729 transcode scenario and how many channels we get. If you compare it to an Octasic or an Advantech DSP, you can see already it's higher performance running G729. You're able to get more transcodes through. If you compare it to an NVIDIA M60 or the new Tesla P100, even substantially higher performance coming out of it. And then compared to an Intel GPU, which is, the reason this is particularly interesting is because all the new Intel server chips effectively have GPUs built into them. So effectively you're getting it for free as part of the compute cluster. So it's a resource that's available and you can use it. So even though the performance is not anywhere near in the same scheme as NVIDIA, it's still a very useful resource. This is with a very simple codec. I mean, G729 has been around for many, many years. If we get to a more complicated codec like 722 or AMR wideband, now you can see where the modern GPUs really excel. So 300% of an existing, or effectively almost definitely 300% of an Octasic DSP. So massive difference in capacity between them. And then what I haven't shown is really the trump card in this is effectively the cost as well. Right? If you compare the cost of a DSP versus the cost of a GPU, it's not even in the same league. A lot of people say, well, it's great. But believe me, we get naysayers on this all the time. Surprisingly, you go, well, I don't see why. It seems like pretty obvious. But if you don't have that intellectual property, of course you've got to kind of defend against it, right? So no, the number one naysayer is, well, where do these things exist, right? GPUs are fine. I've got one in my home computer that I use for gaming, but where can I find them in the cloud? The reality is these are already in the cloud, right? Especially in the public clouds. AWS, Google, IBM Software, they all have GPUs available today and are paid per compute or in a dedicated resource. And more are basically building it into it. And as I mentioned, with those Intel complexes effectively having it in there automatically, it's a resource for use. It's, of course, great for audio. You can see we get 3.5 times the capacity, right? 9 times, as I mentioned, 10 to 9 times versus a regular x86 CPU, and less than twice the of a regular DSP. And if you compare it rack unit for rack unit as well, it's almost twice as efficient as what you get out of a DSP. So we like to call this the DSP of the data center because it's effectively available, ubiquitous, very high performance. So this is definitely an area where we see, as everything moves to NFV, from a media plane perspective, GPUs are definitely the future. So with that, I'm going to shift gears and talk about securing real-time communications. So up until now, I've talked about how we assure real-time communications, how we have high-quality real-time communications in an NFV environment. And now I'm going to talk about the actual security part of it, which is obviously very topical in today's world, right? Cyber attacks are more and more every day, so it's really critical that you're able to secure it. What a lot of people don't realize is voice is kind of one of those things that, because we've always been often like a silo from the rest of the IT, used to have private lines coming in, etc. People don't realize the level of fraud that exists in voice. So in 2015 alone, there was 38 billion in toll fraud. So pretty massive number. And typically, whenever a DOS attack happens, right, that's loss of business of $100,000. So that's per new star. And DOS doesn't just have to knock off your website, right? DOS can knock down your contact center. DOS can knock down your effectively your agent portal. And that will still, that in that case, of course, is TDOS, but that will still cause a massive outage for a particular company. So it's a real problem, right? Denial of service. So between fraud, denial of service, and then I'll talk more about exfiltration, we have a real problem on our hands, right, as a community to solve. And the amazing one to me too, 51% of telephony-based attacks last year was using SIP, right? So we all know SIP is well mature at this point, but we have now finally crossed the inflection point where the hackers are also using it to effectively attack. That problem, of course, is only getting worse. Why is it getting worse? The biggest difference being, of course, the move to SIP trunks, right? Here in the US, we're pretty much, that's really your only choice. Pretty much the same in the EU. I can remember 5 years ago getting up and saying, oh, SIP trunks are at 20% penetration in the US and 3% in the EU. Within 5 years, we have shot to over 70% penetration in the US, and we're in the 40s plus in the EU and others. Yes, there are developing nations that are still behind on this, but effectively, SIP trunks are here, the shift is there. You could hack a PRI, right? A lot of us in the industry that knew how they worked, no problem. You needed physical access though, right? And that was something that made it a lot harder because you needed to actually get access to the network. Just like with SS7, you needed access to the network, and it used to be a very nicely closed circle. Now the trust is broken, and effectively, with IP and SIGTRAN, you can get into it. So the move to SIP trunks has effectively put the transport in a whole new level of hackability. So you have all these people that have tools on the IP world that are able to use those tools to go after and effectively now new level to hack into. So we've taken something that was in a controlled unknown security by obscurity scenario, and we've moved it into a transport that everybody knows. And there's tons of script tools, and there's tons of resources that you can use. And that's, you're not immune if you're on an MPLS-based SIP trunk either. Obviously, internet is more susceptible, but you're not immune by any means. So effectively now you're exposed to those IP hacking tools. The move to the cloud has effectively made the border porous. In the old days, an enterprise would go, okay, all I need to do is secure my 4 walls, and I'm good. And then I just dig a moat around it, and then I put a big fence, and then I put an electric fence, and I'm fine because as long as you're on the inside, you're protected. Now what we've gone and done is put half our resources out up in the cloud, whether we put them in AWS, we put them in Azure, we put them in Google Cloud, we're using Salesforce, we're using Office 365 tools, and the data is everywhere, right? Knowing where the particular intrusion points is a lot more difficult because we've moved it out to the cloud. You've effectively increased the attack surface dramatically. Lastly, bring your own device. You used to have corporate-controlled laptops with particular software on them. Now people come, they bring the Android phone, it happens to have a Trojan on it, it logs onto the corporate Wi-Fi, and we've just punched holes all over the place, right? So between basically changing to IP, opening the attack surface, and putting rogue endpoints, we've changed the way that enterprises work. And for that reason, it's made the problem much, much worse. I mean, most attacks today happen from the inside out, i.e. they start with phishing, and then they effectively do exfiltration. So top UC threats, you go, well, Kevin, what that I know about all these threats, but what could actually happen in unified communications? Effectively, malware, right? Firewalls do a terrible job, and the firewall vendors hate it every time I say this, but they do a terrible job of doing their core business, which is looking for malware. Right? Next generation firewalls make a big deal of being able to stop and find malware. And they'll do a great job if it's on HTTP, or if it's on FTP, or even if it's on a DNS port. But if it's on UDP, RTP, or if it happens to come in a SIP message with a MyBlob, they just let it through. Because they don't scan that. It's not something they look at. And often these days it's encrypted. So they're not able to see it, right? Same thing with spyware. Denial of service, which I mentioned, right? Effectively a massive issue there. And then theft of service, toll fraud. Effectively, there is a lot of exploits that can happen within unified communications. How do we solve this, right? Part of the problem is the moment we have a conga line. So we have things like firewalls, IPS, SPI, DPIs, you've got proxies for web services and QoS, you've got SBCs for voice, but none of these guys talk to each other. They all run in distinct silos. They all care about their specific payloads, and they don't actually share any known pieces, which is pretty ironic. I mean, if you think about unified communications, we have a voice and video, which is typical RTC, but then we're doing IM with it, and we're having all this file sharing with all, Slack and Spark and Teams, and all these things are effectively mashing all this together, but the security devices are dealing with them all separately. So how do we solve that? So at Sonos, we believe, and I actually started to see this at Black Hat and at DEF CON this year, that by making these devices talk to each other, so contextually collaborating is the way to solve this. So by having contextual collaboration and actually sharing information between these different entities, this is the best way to solve that. I'll give you a good example, right? The two most well-known, in our space anyway, are the SBC and the firewall. The SBC has a DNA of deep protocol knowledge, right? It knows about every single state when it comes to SIP and HTTP3 and all those wonderful protocols. So effectively, it will take the particular elements from that protocol and copy it over. It doesn't let any of the information that isn't actually legitimate flow through it. So it does real-time transactional policy. It does microflows. So when it says that particular call is G711, it only allows 80 kilobits per second through. And if you exceed that, it rate limits it. So you effectively cannot send a lot through there. If you try and actually send malware, it will effectively get caught by the signal processor or the GPU, as I mentioned before, and stop that malware from going through, right? It can also stop any kind of SIP exfiltration, SIP attacks. It has a lot of control on that side. It does a great job on all the media attack surfaces and all the signaling surfaces. It doesn't, though, have the functions of a firewall, right? Yes, it opens pinholes and stuff, but firewalls can do malware scanning. They can do, effectively, real-time updating of the latest threat profiles, right? They have line rate DPI. They do great stuff on the data world, but these two really don't connect. So as I mentioned, if we make them talk together, it's a true better together, raise the level of context between the two of them. So what does that actually mean, and what does it look like? So what can we actually share between them? So we've broken that into 3 different categories. So provisioning time, session time, and then events. So provisioning time, right, we can effectively take, because within unified communications, there's often a wide range of IPs and ports that then need to be provisioned on the firewall so that that can flow through to the SBC. And we can now share that over to the firewall, right? At session time, we can now actually share those flows, that information about those flows, and what the type is and what the bandwidth is and how that flow actually changes. And then when we actually find a bad actor, so we find an IP or a port that's bad, we can share that with the firewall, whether it's inside or outside, so that we actually make sure that it's blocked on both sides, and then it's blocked across multiple as well. So this is all accomplished with our new product we're in beta at the moment with, called Sonos View. It's effectively a security and analytics platform, and it uses machine learning, and it uses the data that's basically captured from these firewalls, from the SPCs. It bubbles up into the system, and it basically exerts policy on it to actually take it and go from there. good question. So it's a combination thereof. So it's signature-based and it's anomaly detecting. So effectively, it knows that your typical call use pattern, so a known good call, would have a certain answer-seize ratio within a certain time. And when it starts to creep outside that, it'll be flagged and then actually alerted. And the operator can decide, is that actually a malicious event or not, and then block from there. And then it learns from that. And of course, it puts in exclusions for Mother's Day when it's going to get hit from there. So it's a combination of signatures and machine learning to be able to actually, so it does do machine learning. And this was a critical part of it, actually. And why a lot of people go, well, why didn't you guys do this before? Ultimately, the technology wasn't there before to be able to take this information from thousands of SBCs that are generating 1,350 calls per second across massive carrier networks or on enterprises, and be able to actually amalgamate and do those policy decisions. So effectively, as I mentioned, it pushes it down and around, so you're able to, and that is two-way. So the firewall can also tell the SBC about a bad actor as well. A couple of applications that we actually have running on the system, and I'll jump, since we are short on time, I'll jump to a little quick video after this. So we can look for robocalls, we can look for telephony to live service, we can look for fraud, right? Whether it be a premium number, a lot of numbers, out to the Caribbean, etc. Often that way, we can share the different pieces from it, and the devices can act as sensors and enforcers to be able to push that down. So let me quickly just take you over to the video here, so that I can. So what you're actually seeing here is the control console for it. And you can see I've got configured basically a Palo Alto firewall and one of our SBCs at the same time. And from the SBC, it's talking SFTP, which is pulling out the CDRs from it. And then it also talks REST to be able to apply policies, etc. So if I move forward with this, and I'll, of course. No idea why I'd get an Xbox error when I'm using a media player, but anyway. So just to kind of show you the visualization that you can see of this. So this is, like I was saying, looking for anomalies. So you've got bids, which is basically a call that's been made, completions, call duration. Anybody that knows anything about telephony can see these. This is currently running from a load generator. Oh, fantastic. Thank you. Saw any of that. So this is the configuration for REST and FTP, SFTP I was talking about. And basically now what you're seeing is the dashboard actually showing a view of what's currently being processed, as well as this is the abnormal disconnection. So this is probably the fraud state that's happening. So here we can actually see particular incidents, right? So we've got CAC threshold exceeded, excessive registrations, mail messages. These are all the pieces that have come on there. So if I actually have a look at what it's going to, what that looks like. So this is the incident table. So an incident has actually been recorded on this device. In this case, we're seeing excessive registrations. So this is probably somebody trying to break into the system at the moment. So they're probably basically hitting us with SIP-vicious or something that they're trying to do excessive registrations. And that gets flagged by our SPC. So we can see that this is the remote IP of the device that's actually doing it. We're looking on our SPC in this case, and we can see, yep, it's effectively a registration failure. That's now been fed up into the analytics platform. So the analytics platform now gives us the ability to actually apply. So we can actually say we want to block that IP address, right? So say, okay, I'm going to block that IP, and we apply that. Now looking at the actual firewall, to start with, these are just the whitelists to allow the traffic through. Now when we refresh, we'll actually see that the system has now actually applied through into so it's still only got the whitelists. and it will actually apply that blacklist over onto the, so when I refresh this guy, so you can see at the moment it's not applied. I'm going to go in, I'm actually going to mitigate it, so I'm going to block it. So the system now says it's mitigating. So what it's doing effectively now is it's actually pushing through REST to the firewall. It's updating its address group to say this is a bad IP. Now it says the mitigation status is complete. So if I have a look under the dynamic threat exchange, which is the next tab down, it will show that it's now pushed that through to the Palo Alto firewall. Now if I go back to the firewall tab, I normally prefer to do this live, but you never know with connectivity, so I did a video instead. So if we refresh now, you see it's actually added in an additional entry for the blacklist. So now what it's done is it's actually blocked that particular IP. Now the big advantage of blocking it in the firewall versus blocking it just in the SBC is that this could now be protecting a much larger part of the organization, right? Can keep a lot of additional traffic off there. And you can see in the objects, it's also got the security group there as well. So once you actually make these two guys talk to each other and you use machine learning to pick this up and do it, it's a lot more, you're raising the security context, right? You're making it a lot more powerful. So hopefully that gives you a very quick, short introduction to how we can make firewalls and SBCs really work well together. And so just to sum up, as I mentioned before, tuning OpenStack for performance, using GPUs for transcoding, and then really bridging that security gap can really make us and raise that threshold of real-time communications. So, any questions? I know I've run out of time, but yeah.
So is this an integration with existing firewalls, or?
Yes. Yeah, so we use existing interfaces for everything on this. So, and this Sonos View platform doesn't just work with Sonos SBCs. It'll work with Dialogic, and it'll work with audio codes, it'll work with Acme Packet, etc., or Oracle. So, and it uses the existing interfaces. So I showed it with Palo Alto, we work with Fortinet as well, and whether it be Checkpoint, Cisco, etc. So it uses the existing APIs that are available for these firewalls. Great. Thank you very much. Hey, sir. All right, just turn this off. Yeah.
This is your power. Yeah. Okay, cool. I just make sure I don't steal anything. Guess you guys are all leaving, so this is the added session. So. Cool. So this is going to be an interesting session because I think we're going to have more of a dialogue than actually a presentation. So we actually had a little slide here at the end of the day, at the end of the SDN session, and one of the last meetings we were talking about it, we said, why don't we talk a bit about SD-WAN? So what I thought we'd do today is I'm going to go through a few slides and kind of characterize my view on what SD-WAN is and kind of what the options are. And then we've got a kind of a really cool, rapidly assembled panel, and everybody may not show up, but we're going to talk a bit about it. Because what I'm going to ask is really the question about whether or not SD-WAN is something that's really important, or whether it's just some sort of an interstitial gap till SDN actually takes over. So with that, actually, let's see. There we go. So these are some interesting statistical data. Enterprise WAN traffic doubles every 2.6 years. So it's not quite Moore's law exponentially, but it's pretty close if you look at it. And the number of devices double every 1.8 years, which is essentially Moore's law. So you stop and think about that. This is what the IT professionals that we're delivering solutions to are trying to deal with. And it's pretty scary if you think about it, because most things like bandwidth or device support are actually linear costs. In other words, if you double your bandwidth, you pay twice as much money. And so they're dealing with a pretty interesting challenge. The other thing that's happened is more and more we're moving applications to the cloud. And the problem is when you move an application to the cloud, how you get to that application becomes pretty significant. And is it a hairpin? I'll talk a bit about that. Or is it the fact this is where you're located on the network? So, you know, this is an interesting statistic. I think it was actually came from, it was Gartner, one of those guys, that they perceived, that they said bandwidth would impact over 50% of cloud implementations, have some impact on getting the service out of the cloud. I'm not going to go through this, but this is just a bunch of things that you hear from CEOs or CIOs. You know, my CXO can get 10 times the bandwidth. I mean, I go home and I run speed test on my Comcast internet connection, and it hits 200 megs. CEO of a company runs that and says, why does that cost me $50 at home and you're telling me I've got to buy an MPLS pipe for $20,000 a month? You know, it's those kind of things that really get into people. The real problem is that what we have in our industry is a real battle of SLA determinism and cost. So if you think about SLA determinism, what is SLA determinism? It's just how deterministic is your SLA? So an absolutely deterministic SLA would say, I will deliver your packets within this amount of time, absolutely 100%, never an error. Now, clearly, you can never really achieve that because there are physical constraints of how things work that reduces below that. But, you know, a 5.9 SLA says you're only out 5 minutes a year. So a 99.99% delivery rate has a specific characteristic to it. The problem is that if you think about what's the most deterministic thing you can do to move data around, it's a physical media, a wire or a fiber. Then you go to TDM circuits, actually incredibly deterministic. I mean, not necessarily very elegantly implemented, but very deterministic. Then you get MPLS. What's interesting is there's nothing between MPLS and the open internet. And the cost is very much a reflection of SLA determinism. You know, from you guys' perspective, I'm not going to spend a lot of time on this slide. It's really more for folks who don't understand this, how SDN comes about. What I think is really exciting is what's coming in SDN. So I get really excited when you look at SDN. I look at, for example, if you go back probably about 2 years ago, Microsoft and HP did a demonstration of a northbound SDN interface that could request an ordered pair of IP addresses and port addresses and get a specific class of service applied to that media flow. So that, you know, that's actually, we've demonstrated in this industry. We also know that we have these east and west bound interfaces coming. So, you know, if you think about what the promise of SDN is my enterprise application call server here talks to the control layer, says, I have 2 IP addresses. The control layer realizes one of those is on my network, but the other one is somewhere else. So what it does is it goes to its carrier, adjacent carrier, and says, I need to find that other IP address, and I want this class of service. It continues on until it gets to whoever owns that device, and then you build a connection. I mean, if you stop and think about this for a second, guys, this is a brilliant architecture to solve a huge set of problems for us as an industry. The problem is, the real question is, how long do you think it's going to take to get there? Because 3 things have to happen, and 2 of them are actually really easy, and 1 of them is really, really, really hard. First thing is, we as an industry have to adopt these northbound interfaces, which means that the controllers have to have a northbound interface, and the applications that are used services have to talk essentially southbound that northbound interface. That means, you know, everybody's got to agree. The Cisco controllers, all the other controllers have to talk to Microsoft, have to talk to Avaya, have to everybody. So we all have to agree on what this is to make this work. The second thing is, at a technology level, we've all got to agree on how those eastbound, westbound interfaces and get them implemented between carriers. You've got to agree and get them implemented. That's easy. We do that easy. Piece of cake. Almost as easy as having healthcare. Not quite. That's not the hard problem. The hard problem is financial reconciliation. When I request from my carrier that they deliver that quality to that device, and there's another carrier here and another carrier here, and who's going to pay for that premium service? How does the compensation flow through the network? And this is a huge issue we're not even talking about yet. And until we resolve the compensation issue, yeah.
What, do you think that it's difficult to get an agreement on how that is going to work? Is that why it's difficult? Business negotiations?
So this is
or the technology?
where I say, I want to do that, and this guy's going to reflect back and say, well, it's going to cost you 50 cents to do that. And so I'm sitting here, and I've invited you to pick your favorite IP meeting. I've invited you to your favorite IP meeting, and I sit up, this application says to this guy, I want to get that. All of a sudden, you find it's going to cost $1 to invite you. Who pays the dollar in my enterprise? Do I pay it? Does my IT guy? I mean, you're going to see all these issues that come out. So the concern is this something we're going to see in 3 to 5 years? It's not something we're going to see in 1 or 2 years. It's probably 3 to 5, best case. So here's the argument for SD-WAN. Oh yeah, no, I understand. By the way, guys, just so everybody understands, I'm being incredibly personally optimistic that this is a great thing. If we can get this to work, it's good. By the way, I'll tell you, my argument is eliminate the business. If it were me, I would totally eliminate the business issue. As an industry, you can solve this. I said it here 3 years ago. Just give us 10%. Allow everybody to mark 10% of their packets that they input to the internet as acquiring premium service. It needs to be transmitted at the root core characteristic of the network. I never, always transmits first, never discard. So 10% you'll never have more than 10% real-time traffic. So that's a way to resolve a business issue. We can talk about that in a little more detail. But so here's what the SD-WAN guys are promising CIOs. So I walk into a CIO who's spending millions of dollars on MPL and stuff. Bandwidth is doubling every 18 months, 24 months. And they're really worried about what to do. And I walk in and say, yeah, but I can give you SLA determinism that looks like this for a price that looks like this. This is the argument. The argument SD-WAN is not a technical argument. It's actually a business argument. So how does it work? Very simply, SD-WAN takes advantage of something that Vonage actually bought way back in 2003. They bought a company that had done multiple IP paths for VoIP and integrated as part of the Vonage core. That's really all it is. So if I go to make a connection on the internet, what happens is at the point in time that connection is generated, I bind a path through the internet. As traffic changes, as cute kittens comes on videos and certain links load up, I stay on that path. The other thing that is really bad, if you look at it from the cloud perspective, a lot of organizations actually do this. So I go through the internet where there's a lot of variation back to my data center, where it comes out and now it goes over a pipe up to the cloud. So I'm actually hairpinning, I'm actually using the internet, not just up to here somewhere, but all the way back to here, and then hairpinning back up a high-cost MPLS path to the cloud. So it turns out the architecture a lot of us have implemented is really a lousy architecture. The argument for SD-WAN is really simple. You can have multiple connections into the internet, but the real argument is this, is if I keep trying to establish a connection path from point A to point B, I will get different IP paths through the network. If I keep those open, I now have tunnels I can throw traffic in based on the performance of those paths. So what these SD-WAN guys do is they open a bunch of paths, they send packets in, and they look at latency, they look at packet loss, and they decide which path is the best path for which type of traffic. And all of the, call it for lack of a better word, magic in SD-WAN is that decision set right there. So what happens is basically for the traffic that's out, I went the wrong way. For the traffic that's out here, it just flows through those paths. Now, the other thing that's really interesting is you still can have the MPLS down here if you want it. It really doesn't have to disappear, but it can still be there. The other thing that it does is that this cloud up here can now run through and through the SD-WAN bring it into the data center directly. So that's the other argument that you'll hear the SD-WAN folks make is where do they connect in? What data centers do they have presence in? What data centers can they connect you to? So basically what happens is really simple is the call server, you can take the call server information, the call server generates the flows. The SD-WANs are not doing a northbound interface. They don't have that. What they actually do is they do deep packet inspection to decide what to do. So if you look at SD-WAN today, there are 4 options that are out there. There's a premises option, there are 2 over-the-top options, and then there's the access MPLS carrier option. So over premises is really simple. You just buy 2 boxes that do SD-WAN, you put them on your premises, they go over the open internet, and they do the multiple paths. And there's nobody else involved but you and your equipment. Over the top basically has a carrier network, a service provider network, where there are POPs, that the traffic goes to the POPs from your premises, And then between the POPs, they either use an internet-based interconnect, i.e. they use SD-WAN capabilities across the internet, or they use a private interconnect. And then the last group are the access MPLS carriers, because these guys are jumping on the bandwagon because it solves a bunch of problems for them. Even if you've got an MPLS pipe to your premises, they can use the SD-WAN to go to your branch offices. They can use the SD-WAN to reach into territory where they don't have a presence. And they let you do this over local ISP access. I got to tell you, so I live in California, we have Comcast. Comcast runs ads on KCBS, the kind of news radio, all the time about how great their business service is. It's really cheap to get a Comcast business pipe. Now all of a sudden you can turn that into a much more deterministic pipe with SD-WAN. The other thing that I think is really interesting is what is the endpoint. So if you think about a site, one clear thing is you can do a router add-on, where Cisco's doing this in some of their products, adding these capabilities in, either as an appliance or software VM, or excuse me, not as an add-on, as an enhancement. You can add on to the router, put a box next to the router, either appliance or software. This is the next thing I think you're going to see is, as I've talked to a few of these guys, they're starting to figure out that they can do things at devices to do SD-WAN from devices. So if I'm in a hotel room, I now can not just connect in, and it's not just about the pipe to the POP, it's about getting variable paths to the POP. So you actually move the SD-WAN distribution point from the POP out to my desktop. So I'll tell you my conclusions on this. I really believe that SDN, the way we're implementing it, is great. I think it's going to be the right thing, but I don't think we're going to get there in time. I think the pain in the enterprise is really high. I think for the enterprises, SD-WAN is a really exciting solution. They're getting promised essentially 90% of the determinism for 15 to 20% of the cost of MPLS. That's kind of the argument that you're seeing out there. There are SD-WAN solutions for virtually any WAN architecture. Kind of regardless of what you've done, SD-WAN is coming into it. So if you've got MPLS, and you've been doing your branch offices, for example, on T1s, and you start looking, well, we want to go to Comcast, all of a sudden there's an SD-WAN for your branch office. It may not change your core architecture, it just changes the edge. This is the claim, and I will argue that there are people that have tested it, and they say it's pretty good, that it really has the capacity to deliver real-time at SLA levels that approach MPLS. And this low-cost internet pipes. So we have a panel. And I just want to get, does this make sense to everybody?
Yeah, I just wanted to throw one thing in to what you were saying. I'm Joe.
Yeah, Joe. Yeah, so we're going to so guys, we assembled a panel yesterday evening. So why don't you guys come on up, and as far as I'm concerned, why don't we sit here? We don't need to, we just have a discussion if you guys are cool with it. I'm easy. And my intent was not to be too much of a water. We just want to have, thought processes.
So what I was going to add in was that SD-WAN doesn't obviate or exclude the use of some MPLS links. You can reduce the number of MPLS links because you're absolutely right about currently we have a lot of applications which have migrated from back in the headquarters main office out to the cloud. Office 365, AWS, Google Docs, all these things that we love, but what we use. And this certainly doesn't make sense to haul everything back and do a hairpin turnout as you described. And there could be a lot of applications that could use a secure tunnel back, but you might still find organizations that want the benefits of reducing their overall MPLS footprint, but retain some for certain critical applications that might need to be financial, medical, etc. And SD-WAN technology can let you have a mix of those, so you can route everything on the best path, some of which might still be MPLS, at least for a while.
Right.
So it doesn't mean you have to get rid of it as my own.
Absolutely. So, by the way, I did a session on this last week at the SCTC. Sprint there. That's what Sprint said. Their proposition is mix and match, right? Pick what's right, and I would argue that
It lets you rationalize your transport better.
exactly. What I would argue is that one of the things is the time domain of change is actually very interesting. So if you've got a connection that has low time domain of change, then technology like fiber or MPLS makes sense, and it's things like branch office, things that change much more regularly. Maybe this is a better way to do it. But again, it's not a panacea. I think that's what your point is exactly.
Well, and to my point, it also, my initial
know about it. So I can actually monitor the internet in ways that are really interesting. I think we've seen in a couple of years these guys actually start talking about what's happening. You can't hear me, I'm sorry. Gert, you made the comment, you're not nearly as enthused about this. And I don't want to be over enthused. I really want to understand what are the concerns and issues.
Yeah, thank you. So I'm going to go a little bit on a shifting ground here. I know there's a panel with 2 SD-WAN vendors, so I hope I don't get stuff thrown at me, but I'll give it a try anyways. For people that didn't attend my presentation yesterday, so I'm from Microsoft IT, so I'm not part of Azure or any of the business parts. So I don't believe in SD-WAN for a number of reasons. I think they did a great marketing. I think they deliver a great story to a CIO, which they are very capable of. And I can see there are some short-term gains for certain situations. Let me say the fundamental issue that I have with the way they try to classify traffic, and I kind of also addressed that more lengthily yesterday. At the current speed or the current capacity that networks run, it's impossible to do like DPI, deep packet inspection. Trying to classify voice and video traffic, it's a big gamble, right? You can probably classify, we tried it on our wireless LAN controllers, which is obviously at a lower speed than what the wire is, and we think we captured approximately 75%. The smallest thing that happens with a codec, SIL gets introduced, all those kind of things, all those mechanisms are down the drain, right? So you classify 0% of your traffic correctly. Everything is getting encrypted, everything gets SSL, runs over port 443. Trying to break open every packet is impossible at the condition you would have the key. So just the way they're trying to gamble what's in a packet, I think is the wrong way to do it. The only way is, and we just heard it from you, from Charles, from others, the only correct way to do that is have the application talk to the network, which is a longer term solution, but that's kind of where we're going. So that's what I presented yesterday too. The other thing, and this is not really around open source, but at Microsoft you have a clear direction that we don't want to be locked down by any of the vendors anymore. So all these, you mentioned 45 vendors, they all have a proprietary solution. A lot of them are small startups that nobody can tell or guarantee they will still be around in 6 months. Some of them are actually spin out smaller sections into larger corporations with the financial backing. But we also know if that doesn't take off, they easily disappear in the same speed that they showed up, right? So it is kind of picking one of those 45 vendors or standards or proprietary solutions is kind of risky, in my opinion. So that's not the way we want to go as an IT organization. Also, I understand you can have multiple paths through the internet. To take the extreme example, if you're behind the Great China Firewall, if you have a bad internet connection, you know what? You can take 3 different vendors, you're going to have the same issue. In more of I would say the areas with a great internet connectivity, like the Bay Area, the Puget Sound area, even Western Europe where I live, having one vendor in general gives me all the capacity I need, and if it breaks, I pick up my cell phone and I use 4G. Right? That's what people do today. So we don't really kind of invest in that area. I do understand there is a lot of advantages for service providers, for even like cloud providers, where they can say we want a single pane of glass, we want the ease of deployment, we want to make sure that we can go to these areas where we don't have coverage today. So from their perspective, I can see there are a lot of advantages. And like I said, for enterprises, I also can see there might be some short-term gain, but I definitely don't believe in the long-term.
I think you brought up a great point. I'll be really loud. You brought up absolutely a great point, which is, deep packet inspection is a Band-Aid. It's a trust Band-Aid, right? Because we start off with endpoints defining the characteristics they need for service, and they all lie. Because, we all know, the first VoIP system we put in, we had packets marked for VoIP. It was a university, and within 3 months, 60% of the traffic on the network was marked for the diff-serve field that gave the because all the students told all their friends, change your code points. And so you can't trust endpoints. You can't trust the endpoint. The only thing you can trust is that core app. So I think the point you brought up is really good. If you talk to an SDN or an SD-WAN vendor, you have to have the conversation about their commitment to SDN northbound interfaces and how soon they're, and if they spend all their time saying our real expertise is deep packet filtering, that's expertise in what you really don't want. And by the way, 100% agreement. The northbound interface, when I first saw that concept, it was like, wow, this is the solution. Any other comment? Yeah. This is supposed to be conversation, so. Hard with one mic.
I didn't write, oh, okay.
So,
Well,
any questions, thoughts from folks in the audience? Does this make sense?
Yeah, I mean, I would agree with Gert. I think you brought up great points. To me, SD-WAN, the whole idea there is, yeah, you want to be able to classify this traffic somehow. And like you mentioned, that's sort of the critical thing. And if you're relying 100% on deep packet inspection, that's a very, very brittle and, in fact, expensive solution, right? Because you got to be able to get into those things. And it's going to get harder and harder to do that. Not only do you see people marking their traffic, say, differently, disguising their traffic so it looks like something else, tunneling everything over, within HTTPS so that you don't know what's there. Even DNS, right? That's going to be running over HTTPS very soon. In some cases, already is. So that's a losing battle. Yeah,
Traffic's becoming opaque. I think what you're saying is deep packet inspection is hard. The SLA that you get may be more dependent upon the validity of the deep packet inspection than on the actual operation of the network, right? How you
right, which is a big problem. So rather, you need to classify the traffic somehow, and how you classify the traffic, there's better ways of doing it. The application telling you is a great way. The endpoint being able to tell you. I mean, also, in some cases, YouTube's going to be incredibly important to me, and so the fact that I could even be having a video conference, a video call with you, and watching YouTube at the same time, and sometimes I really don't care about seeing your video because what we're talking about, I mean, no offense, but what you look like isn't changing, and what we're actually
a lot less about how I look. I'm more worried about the attention.
what we're having a conversation about is directly impacted by this YouTube feed, right? Maybe we're handling an emergency response situation, and we see there's a lot of limitations there. But imagine I'm getting a video feed from some streaming application, and being able to see that and talk to you about it is a lot more important than being able to see you. So in that case, the priority is totally, it's not static, right? So, and it's having these programmatic interfaces that allow you to do things that used to require manual effort, and now the fact that you can do them in an automated fashion. Taking advantage of that is to me the key. And in order to take advantage of that, those interfaces need to be open, right? Proprietary solution, completely agree, that's going to fail, or I think Gert brought that up. In order for it to work well, these need to be open interfaces. They don't necessarily need to be an open source solution. I'm a big fan of Open Daylight as, say, the controller, but as long as what you're using, say, as your control point has open interfaces that other people can talk to, and if they're standard interfaces so that you don't change them and break all their solutions, yeah, then it can work quite well.
Yeah. Right. Well, and I think
You could build to have high quality on both links, or you could say, okay, I'm not going to exceed my budget here, but it's much more important that Phil and Charles both be able to see the third thing they're talking about and see each other, and I would just like to see the priority.
So contextual, you actually brought up the point of contextual, which is really interesting. So years ago, we were doing VoIP for a big Western bank, and they had a T1 into every office, and they were using, it was 3G cellular as a backup. And we started talking about what happens when you go to the cellular backup for voice traffic. And the guy looked at it and he says, I don't want any voice traffic on the cellular backup. He said, when we're on the cellular backup and we lose 70%, 80% of our capacity, the only traffic that's important in a bank branch is the traffic that gets people out of line talking to tellers. I mean, it's a really interesting thought process, right? In normal operation, voice is high priority, but when you go into a reduced capacity situation, it has zero priority because the thing that has most priority is getting people out of line from the tellers. If you slow the tellers down, it has a dramatic impact on customer satisfaction, where most of the calls to the bank are not customer satisfaction oriented calls. So coming back to your point about, it's exactly the same case as wanting to watch the video. People have to be able to characterize it. And if the deep packet inspection doesn't understand how to do that well, it's going to blow up. And your SLA you think you're getting that's demonstrable at a core basis is not being extended to your real applications, which is why the northbound is so important.
No, I wasn't disagreeing. I was just, but I wanted to make another point which sort of follows on to what you were saying, but I was waiting for the hook. So one of the things that I've seen, I've got two hats here. So with the MEFs, I'm co-leader of the MEFs SD-WAN effort, but I also work at Riverbed. And in both places, I talk to a lot of customers. So I'm not going to say who, but there have been those who have bought the promise of SD-WAN, and then the reality has been delivered, and lo and behold, there's a little bit of a gap. Or, for example, they perhaps downsize their IT staff as everything moved to the cloud. Then they brought in SD-WAN and discovered that they were taking back upon themselves a lot of responsibility that had once belonged to their service provider. Oh, wait a minute, my apps don't perform like you said they would, Mr. Vendor, or I have to hire more IT guys to keep my SD-WAN policies and everything ticking over as well as it used to. And we're seeing in both places, in fact, I had a customer who won't let me quote him, but he gave me a line about, I want the benefits of this SD-WAN stuff. I want to reduce my cost on MPLS circuits. I like setting policies. I like the ease of turning up branches and all that. But I want to outsource the pain of maintaining the thing to somebody else. And I would like one neck that I can choke when it goes wrong. And I'm curious if you have any thoughts about that sort of business evolution of this. So there's been a lot of promises made. 1,000 flowers have bloomed. How do you think it'll shake out?
I think you're actually emphasizing what's on this slide. I mean, what you're saying, like SD-WAN kind of started, to my mind, over here with the guys that were kind of building competitive. It's kind of started as almost an extension of the guys who were building WAN optimization stuff.
Hey guys, we have some tunneling in the barn.
Right. Exactly. But what's really happened, if you look now, the hot spot is a combination of here and over here. So you've got guys like, the 128 technologies guys. You got like VeloCloud, who are actually selling here, but they're also selling over here. So I think what's happening is a lot of the action is moving over here to having that service provider presence and being a service provider and positioning as a service provider. Because you're exactly right. SD-WAN doesn't take away what the service provider was providing you. So, and that's a really interesting question, because if you're a company, what do you do with SD-WAN? Who do you talk to? And everybody's going to tell you, lots of people will tell you they have it. So.
It was interesting, a couple of days ago, we had Alan Quayle, railing passionately as only Alan can against the evils of service providers, but businesses discovered that, well, wait a minute, I do actually want a responsible party I'm paying money to make the problem.
And isn't it absurd that we're railing against service providers while extolling the virtues of cloud? I mean, just stop and think about it for a second. Pretty orthogonal in that concept. Anyway, any other comments, questions? And by the way, we can just quit whenever we want, because this was an optional free session. So if there's no more questions, comments, we'll just call it, and we'll have a little bit longer break till the keynote. Goodbye.